Greetings, physics enthusiasts. Welcome to AP Physics 2, Unit 7, Lesson 1. Unit 7 is called Quantum, Atomic, and Nuclear Physics. It's a lot of different things. Quantum physics, atomic physics, nuclear physics. So it's a lot of different things. And we're going to go through 6 different chapters in this unit, and we're just going to do little sections of different chapters in your textbook. So it's kind of advanced topics, we could call it. That might be the title of a course in college. Advanced topics in physics. It means the stuff we haven't covered yet. So let me just tell you different things we're going to talk about in here. We're going to talk about light. We just finished optics, where we talked about how light bounced off of things and traveled through things and interfered. And so we're going to talk a little bit more about light. Right now, we're going to talk about light as a wave and how fast it travels and what the nature of that light wave actually is. So have you ever heard the phrase electromagnetic wave? I bet you have. Light is an electromagnetic wave. Well, we've said before that light is a wave, meaning that, it can, one wave can interfere with another constructively or destructively. But another thing about light is that what kind of wave it is electromagnetic, which has to do with an electric field, and it has to do with a magnetic field. Well, we've studied electric fields, which we abbreviate with a capital E, and we've studied magnetic fields, which we abbreviate with a capital B. So it turns out that light is an electromagnetic wave. What does that even mean? I have a picture that I would love to share with you, and maybe that will help us all understand. So this picture, which is very small on my screen. There we go, now it's bigger. This picture shows, I can't point at this for you. Anyway, it shows an electric field, which is represented in that orangey color, and it shows a magnetic field represented by that blue color. And you'll notice that the electric field, starts with a number of 0, and it gets bigger and then smaller, and then it changes direction. Then it points down more and less, and then it points up more and less. And while the electric field is oscillating, this picture is 3-dimensional. So while the electric field points up more and then less, and then down more and then less, and then up more and then less, the magnetic field is pointing out of the page more and then less, and then into the page more and then less, and then out of the page more. So what is happening is as location changes and as time changes, the electric and magnetic fields change. So the wave is not in all of these places all at once. The wave is here, and then a moment later it's 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 here. So this changes with time, and then as time goes by, the wave is in a different location. So let me stop the share for a moment, and you're looking at me. So as the electric field is getting greater and less vertically, the magnetic field is getting greater and less horizontally. And while that happens, the wave propagates, or the wave moves forward. So it looks like this: bigger, smaller, and then other direction, bigger, smaller. So that's something that you could practice while you walk across the room. With one of your hands, you're going to go up and down and down and up and up. And with your other hand, while this one's going up and down, this one's going horizontally. Farther from you, closer to you, farther from you, closer to you, farther, closer, farther, closer. And you're doing that while you're walking forward. And that's what it's like for a photon, for a piece of light to propagate. So so practice that. This would be a great time to press pause and just practice that. You know, I'm an electromagnetic wave. I'm a piece of light. And you're doing this, and then you're doing this, and this, and this, and this, and this. And one of the things you'll notice is that the electric field and the magnetic field are zero at the same time. And then they grow, 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 and then they are maximum at the same time. And then they decrease and they are zero at the same time. And then they increase in the other direction and they're maximum at the same time. And then they decrease and they're zero at the same time. And so on and so forth. Okay, so practice that physiological movement, that kinesthetic activity is what we call kinesthetic learning, and it will help you remember things in a different way. Another way of practicing this is trying to redraw that picture. So let's pick 3 different colors. I know, you know, it's going to be purple and black and green. So here is the space through which the electromagnetic wave is going to propagate. And then I'm going to use one color to represent the electric field. And these little arrows represent the strength or size of the electric field when we're at that exact location. Pardon me. So I'll use purple for E. And then I'll use green for B. And I want this to come out of the page and then go into the page and then come out of the page, but I can't draw off the page. So what we do is we draw just a little bit off center like this. Now, I'm not doing nearly as good of a job as the book did of indicating that. But you can also draw these little arrows this way. And then all of a sudden, this does look like maybe these two planes are at right angles to each other. So try practicing drawing that. Those of you who are less terrible at drawing and art than I am will probably be more successful. And that is B, my magnetic field. And the wave is propagating thusly to the right. So the electric and magnetic fields are always perpendicular to each other for the top of the page, out of the page. Not only are they perpendicular to each other, but they are also perpendicular, each of them is perpendicular to the direction of propagation, to the direction that the wave travels through space. Pardon me, I got phlegmy. So that gives us an opportunity to say one of our favorite phrases, mutually orthogonal. It just makes things feel smart. When 3 things are perpendicular, each of those 3 things is perpendicular to both of the other 2. We say that the 3 things are mutually orthogonal. So the direction of the electric field, the direction of the magnetic field, and the direction of propagation are mutually orthogonal. Now, they're mutually orthogonal in a specific direction as well. If we get out our right hand, not our left hand, don't use that one. If we get out our right hand and just go like this, and then like this, oh, and then look at our thumb. So fingers up, fingers bent, thumb. That's the order. Fingers up, fingers bent, thumb. And then say E, B, I'm sorry, E, B, V, E, B, V, E, B, V, E, B, V. So if you say that over and over, E, B, V, in that order, if my fingers point in the direction of E, and then I make them point in the direction of B, E, B, oh, my thumb points in the direction of V. Did that work for this one? This is supposed to be pointing down. E, make your fingers point down. Now I could make my fingers point down this way, E, but then B is that way. Ooh, that hurts. I can't do that. So I have to have E, B, oh, V, still pointing in the correct direction. So E, B, V, or E, oh no, it's got to point into the page. E, into the page, V. So that's another way you can use your right hand to remember some of these directions in physics. That is a right hand rule for E and B and V. The right hand rule. One more thing about this equation, and then we'll move on to something else. We said that E and B are 0 at the same time, 0 at the same time, 0 at the same time, 0 at the same time. And they are also maximum at the same time. It turns out that the ratio of E to B remains constant. They both grow, so one divided by the other is the same at every different moment. And it turns out that that ratio is always 3 times 10 to the 8th. Whoa! Which we remember that number is the speed of light. And it turns out you can, I will leave this as an exercise for you to do on your own. And if it turns out it's too hard, which it's not, you can always ask me to show you in class. But the unit for electric field divided by the unit for magnetic field is meters per second. E over B is a speed. What speed is it? It's the speed of light. Oh my goodness gracious, that's exciting. Isn't that exciting? So E over B, the electric field strength divided by the magnetic field strength at any moment will always be this same number, 3 times 10 to the 8th. Now, some of you are saying, but what about here when they're both 0? Yes, 0 divided by 0, your math teachers are having a fit. At that moment, their ratio is undefined. But at every moment where the numerator and denominator are not both 0, the ratio of E to B is always 3 times 10 to the 8th meters per second. Super cool and fun. And of course, we talk about the speed of light, 3 times 10 to the 8th meters, so often, 3 times 10 to the 8th meters per second, so often that we give it a letter just so we can be lazy and abbreviate it. Small c is the speed of light. Okay, so that is why we say light is an electromagnetic wave, because it is an electric field and a magnetic field. It is oscillating fields, one going up and down, one going in and out, propagating through space. All right. Enough about that. Let's talk about a couple equations. We just talked about C equaling E over B. There is another equation for all waves that the speed of the wave is equal to the wavelength of the wave times the frequency of the wave. And so that's true for light waves as well. C, the speed of the wave, is wavelength times frequency. So just remember that. Light can have different wavelengths from very, 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 very small to, more than a meter. And remember that if it's visible light, just fun to remember, visible light, the light that our eyes can see. Invisible light, there's nothing really magic about invisible light. It's just light that our eyes are not capable of noticing. So invisible light isn't so much magic, it's invisible. It's just pointing out the deficiency in this particular detection device. Visible light is around from 400 to 700 nanometers, or 400 to 700 times 10 to the minus 9th meters, which is around 4 to 7. I made these numbers smaller, so I have to make this number bigger. And the way I make a negative exponent bigger is times 10 to the minus 7th. Actually, a smaller number, smaller in size, but less negative, is bigger. 4 to 7 times 10 to the negative 7th meters visible light. 400 to 700 nanometers. It's just something that people tend to know. The small wavelength and small wavelength turns out to be larger energy. And larger energy also tends to be larger frequency. Well, here, see, they all have the same speed. So if one of these gets bigger, the other has to get smaller because the product has to remain the same. So small wavelength should be large frequency. And the two things that are both large together is frequency. So remember the electromagnetic spectrum, red, orange, yellow, green, blue, purple, right? So red, orange, yellow, green, blue, and then I don't know what, indigo and violet, but I just call it purple. So Roy G. Biv, the 400 end is the large energy that corresponds to violet. And the long wavelength corresponds to the red. That's good stuff to know. In fact, this list, this is called visible light, but there's stuff on the other end, smaller wavelength than 400, and there's stuff over here, larger wavelength than 700. And that whole collection of light is called the electromagnetic spectrum. We said light was an electromagnetic wave, so the electromagnetic spectrum, I'm a much better speller when I'm not talking. The electromagnetic spectrum is just all the light from small wavelength all the way up to large wavelength, or from small frequency all the way up to large frequency. Did you see what I did that? I said small wavelength to large wavelength, or small frequency to large frequency. All the way along the spectrum, large or small wavelength or frequency, the speed is always the same, 3 × 10⁸ meters per second. Now, I have a picture here I want to show you of the electromagnetic spectrum. It's a nice picture in my textbook here. So let's zoom in a little on that. And in your textbook, you might find it on page 716. But look at this. We have frequency listed on the left, and we're going from small frequency down here, 1,000 hertz, 1,000 cycles per second, all the way up to really large frequency, 10 to the 22nd cycles per second. That's a lot. The wavelength, this was big frequency, so this is small wavelength, less than a picometer. Goodness gracious, pico means 10 to the minus 12th. Remember, like Pico Avenue, which I call Trillionth Street. And then nano is also still really small, but it's 1,000 times bigger than pico. And micro is really small, but it's 1,000 times bigger than nano. And milli is really small, but it's 1,000 times bigger than micro. And then meters, and then we even have waves that are not, so these are trillionths of meter wavelength, and then thousands of meter wavelength. So we go from really, really long to really, really, really small. So increasing frequency, increasing wavelength, decreasing wavelength, decreasing frequency. As I go this way, I'm increasing in frequency and decreasing in wavelength. As I go this way, I'm increasing in wavelength and decreasing in frequency. Talking through that and saying those relationships is wonderful practice. I'm not saying those things so that you can understand them and memorize them all right away. I'm saying them to model for you how you can talk about this. And as you do that talking, as you try to repeat the things I say or say things similar to what I say, that is how you study and how you understand and how you remember. So you really should go through and describe what this means. Is this an increase or a decrease in what? Is this an increase or a decrease in what? And while that happens, Does this increase or decrease? And what is it that's increasing or decreasing? Okay. Now, memorizing the actual numbers like 400 to 700 nanometers. Oh, look at that. I memorized it right. I said 400 to 700 nanometers too. Good for me. Yay, Davey. But this, I mean, it's blown up here, but look how tiny that little bitty region that we can actually see is. Most of the electromagnetic spectrum is not in the visible range. So, red, orange, yellow, green, blue, violet. Look at what's right next to the red end, infrared. And look at what's right next to the violet end over here, ultraviolet. Well, that's pretty easy to remember. Ultraviolet's right next to violet, and infrared is next to red. And I like to remember that ultra means more. So this is the more end, and infra actually means less. So this is the less end. Now, what is it more or less of? Well, we're getting more on the frequency side and less on the frequency side. So this infra and ultra is referring to frequency, not to wavelength. We're not talking about more wavelength. No, we have a smaller wavelength here. And we're not talking about less wavelength, we're talking about more. So remember that this infra and ultra, that those prefixes refer to the frequency side of the scale, not to the wavelength side. Ultraviolet, and then even greater frequency is X-rays, and the greatest frequency is gamma. Those are just really helpful things to know. I don't encourage a lot of memorization, but that's really good to know. And you know, how hard is it? You already know Roy G. Biv, and infrared and ultraviolet, that's not hard. So you just have to remember ultraviolet, and then even higher frequency X-rays, even higher frequency gamma. Infrared, even lower frequency microwaves, yeah, like the microwave oven. But the microwaves are pretty close to micrometers, right? And then there's these television and radio waves are down here. So if you remember infrared, micro, and radio. And you'll also notice that these overlap. These are not mutually exclusive categories. This wavelength or this frequency could be called infrared or micro. This could be called micro or radio. These could be called gamma or X. But just knowing the order is not really hard, and it could be helpful as you move along in life. All right, so that is called the electromagnetic spectrum, and it's just a lovely picture right there. Now I have two more equations to talk about with you. One of them, I'll tell you the equation and I'll tell you about it. E equals HF. So there's the frequency. Remember, we said the speed of light is the wavelength times the frequency. Well, this is the same F here. Remember, I told you that light is a wave, but we could think of light as a particle as well. And I'm going to prove this to you a couple lectures from now, so don't worry about it. But if I think of light as a particle traveling along, how much energy, E energy, does that particle carry? Well, E, the energy carried by a particle of light, is equal to H, this constant, which is just 6.6262 times 10 to the minus 34th, small number, joules times seconds, times the frequency. And of course, the frequency is in 1/seconds. So the 1/seconds in frequency cancels out with this second here, and it gives me an energy joules. This tells me how much energy is carried by one little particle of light. That little particle is called a photon. So I wanted to talk about these two equations together, just because they both talk about light and the frequency of the light. And what that ends up telling us, if E equals HF and H is a constant, That means if F is bigger, E is bigger. And if F is smaller, E is smaller. So when we move this direction, we're increasing in frequency. That means we're also increasing the amount of energy in each photon. Whereas when we go this way, we're decreasing the frequency, and therefore we're decreasing the energy. We're decreasing the frequency, and therefore we are also decreasing the energy of each photon. So that's important to know, that energy and frequency are directly proportional. High frequency is high energy photons. Low frequency is low energy photons. Of course, high frequency means small wavelength. So if large frequency means large energy, that means small wavelength also means large energy. And again, these are sentences that I'm not saying so that you can say, oh, I get it, and never think about it again. These are sentences that I'm modeling for you how you should talk through it to understand it and remember it. Large frequency is large energy, but large frequency corresponds with small wavelength. So small wavelength is large energy. Therefore, large wavelength is small energy. Okay. The final equation I want to talk to you about. This feels a little hodgepodgey, but it's the last equation in this chapter. And it's the Doppler effect. And I know you're thinking, wait a minute, we talked about the Doppler effect when we learned about sound. Yes, we did. And now we're talking about the Doppler effect when we're learning about light. So, when light is traveling toward you, if the source of the light, so if I have a flashlight and I'm shining it at you and I run at you, or if I have a flashlight and I'm shining at you and I run away from you, you're not going to see the same frequency. So I've got a flashlight, let's say it's a laser and it's emitting just one frequency of light. If I stand still and you stand still and I shine the laser, you're going to see a certain color of light, a certain wavelength of light, a certain frequency of light. All those are the same thing, color, frequency, wavelength. They talk about how the light wave is changing. Is it this kind of wave or is it this kind of wave? But same laser, if I run at you, just like with the Doppler effect for sound, when the car blows its horn and drives towards you, you hear a higher pitch. Well, when I run towards you with the flashlight, you see a higher frequency light. Higher frequency light. Higher frequency light is smaller wavelength light, and the small wavelength was on the violet end of the spectrum. Whereas, if I run away from you, if a car's driving away from you, you hear a lower pitch, lower frequency, and lower frequency corresponds to greater wavelength, which was on the red end. So you've got to be able to talk your way through that because I don't want you to memorize it. So when there are stars out there, here we are on Earth. And here's a little star out there. Twinkle, twinkle. Well, the star is probably not stationary in space. The star is probably traveling either toward us or away from us. If the star is traveling toward us, it's going to emit light. But because it's traveling toward us, we're going to experience, we're going to receive light that's actually of higher frequency than the star emits. Higher frequency. So red, orange, yellow, green, blue, indigo, violet. What's the high frequency end? This is the high frequency end. Well, forget about indigo and violet. We call that a blue shift. So the light looks bluer than it actually is. If there's another star over here, and it's traveling away from us, it emits light of a certain wavelength and frequency, but we experience a longer wavelength, a bigger wavelength, and a smaller frequency. And the bigger wavelength, the smaller frequency end, is over here. So that's called a red shift. So the light we actually end up seeing is redder, or bigger wavelength, or smaller frequency than the star actually emits. And I showed you the equation for that, and then I closed the book. Naughty Davy. 2132. And so that is this equation. F naught equals Fs. That's not a naught. That's an FO for observer, and that's an Fs for source. 1 plus or minus U over C. So this is the frequency of the star, or the source. This is the frequency that the observer actually sees or experiences. 1 is the number 1. C is the number 3 times 10 to the 8th. And then U, that is the speed of the star. Okie dokie. So, and if we're moving toward, let's say we've got a blue shift, and the star is going at a velocity equal to U. Well, if there's a blue shift, I'm seeing bluer light, which is higher frequency. So I want this number to be bigger than this number, right? And therefore, I want this number to be greater than 1. So I'm going to add the speed over C. Whereas if I have a red shift, that means I'm seeing redder light, which is bigger wavelength, but smaller frequency. So I'm going to see a smaller frequency than the star actually observes. So I want this number to be less than 1. So I'm going to subtract U over C. So that's how you decide what to use, plus or minus. All right. And that now is, you understand the additional topics. We're talking about a few different things about light being a wave. I hope that's been interesting for you. I hope you're having a great day. But regardless, don't break the laws of physics.